right? Because of course we have more parts than we have like kind of like sections of parts, right? And so we always have more than, right, what we have. So here, right, 16/7 is at least 2 wholes. And then how many more parts? 2/7, right? 2 and 2/7. And so just like we see that relationship between proper fractions, decimals, and percents, right? For every mixed number, we can represent that as an improper fraction and vice versa, okay? Do we need to think of it as kind of wholes and parts, or do we want to think about it as a fraction? Okay, so there's different times and different situations where we might do that, okay? So this one down here is showing us kind of 4/5. It doesn't give us an equal sign, so we're not talking equivalent, but then it kind of says 4/5, 5/4. Does anyone remember, or what would we put in there?
Reciprocal?
Reciprocal, good. And so once again, another kind of characteristic of fractions is that every fraction has what we call a reciprocal form. I don't think we had to use them very much for ratio or proportion per se, but it will come into play in algebra a lot. And so just kind of be ready for that and just know, okay, if you, and then hopefully you kind of notice, right? If you multiply a fraction by its reciprocal, what would you get as far as an answer? And it would be true of any fraction multiplied by its reciprocal.
1.
1. Good. Good job, Celeste. Yep, exactly, right? And so part of the way of kind of canceling out fractions is using reciprocals, because once again, we make these kind of equivalent fractions that just are ones. So it's not really changing the answer. It's just kind of changing the form. Okay. And then of course we know that our top number on our fraction is called the numerator. And so, good. Any questions or confusion, thoughts about these 12 terms and kind of how we label them, how we're going to talk about them? Does everyone feel pretty good about this?
Yeah.
Good. Okay. So once again, when we just have the fractions, right, we're dealing with them at a very numerical level. If we begin to put units, right, then we're probably using either a ratio, a rate, or a proportion, okay? And we kind of use the rules and characteristics of fractions to show those relationships, okay? All right, excellent. So just for fun, if we look at some of these questions here, it tells us a yard contains 36 inches. So 21 inches would be what fraction of a yard? 21 out of 36. And then remember that our final step here is we should look and see, can we reduce this to a simpler form? Is there a number that we can evenly divide out of the top and the bottom to make it simpler? And of course, if you have your handy dandy calculator, it would do that for you. 7/12. Good, 7/12, right? 3 is our common factor. So I can divide a 3 out of the top. 21 divided by 3 is 7. I can divide a 3 evenly out of the bottom. 36 divided by 3 is 12. So the simplest form. Okay, you're good, Angel. I completely understand. Good. So 21 inches is 7/12 of a yard. Not very useful, but it looks like you guys are doing a good job of, right, put your kind of what we have over what is kind of our whole unit here. And then look at it. Do we need to reduce it to a simpler form? Okay. All right, which of the fractions in this list are less than 1/2? We got 3/6, 7/15, 4/9, and 5/8. And we're looking for less than 1/2.
5/8.
Is 5/8 less than 1/2?
It's 7/15 or 9.
Okay. So why do you like 7/15 and 4/9?
I just chose 2 little.
Okay, good. So yes, so 5/8 is actually slightly bigger than 1/2. And so what you would do to determine kind of the size of a fraction is you look at the numerator in relationship to the denominator. If the numerator is more than half the denominator, like 5/8, right? Half of 8 is 4. So if I have 4/8, I have half. If I have 5/8, I have a little bit more than half. Okay. Why is 3/6 less than 1/2? It's exactly 1/2. So no, it's not, right? It's equal to 1/2. But once again, right, if we look at 7/15, it is less than 1/2 because 7 is less than half of 15. Just barely less than 1/2. Same with 4/9, because once again, we know that, right, 4/8, right, would be exactly half. So if we have 4/9, then we have even less than that. And we end up with a little bit less than half. So that's kind of one of the ways when you come across fractions, right? The further apart the numerator and the denominator are in value from each other, right? The smaller the fraction is, the further away from 1 you're getting and the closer to 0. And of course, if we're even less than 1/2, then we're even closer to 0, okay? All right, so we did some reducing, so hopefully that feels good for everyone. Can anyone write this mixed number as an improper fraction? Does anyone remember that one? All right. So just to remind you guys, you take your denominator times the whole number. So 8 times 11 is 88. And then add the numerator to that answer. So 88 plus 5 is 93. And then just put your denominator back on the bottom. So 11 and 5/8, right, is equivalent to 93/8. Okay, so this would be the mixed number version. This is the improper fraction. Okay, then if we do it the opposite way, right, 12 goes into 52 whole times, 4 times, excuse me, 4 whole times. 12 times 4 is 48. 50 minus 48 is 2. And then keep the denominator. Now, when I look at 2 12s, I then know that I need to reduce that to simplest forms. 2 over 12, I can divide a 2 out of the top and the bottom. So it's 4 and a 6. Okay. So you take your, just divide, and then whatever your remainder is becomes your numerator. Denominator stays the same. Okay. Yes. Well, no, actually you divide 50 into 12. 50 divided by 12. And then you should get 4 remainders too. Okay. How would we change 3/4 into 12ths? So this is kind of like our proportions. So we could say, right, 3 is to 4 as, right, what is to 12, okay? And of course, it's kind of hard to see if I type it like that, but yeah. So you're really just you could, I mean, you could definitely make a proportion or you could just kind of see it, but if it says change this fraction to a different fraction, we know this is our denominator. So once again, it's telling us, right, what is the equivalent form of 3/4 as 12ths, right? So we take our 4 parts and split them up into 12 parts now. So if we had 3 of those 4 parts, how many of the 12 parts would we have? Now, when we worked on proportions, right, we would cross multiply and divide, which would work here, right? 12 times 3 is 36. 36 divided by 4 is 9. Sorry. Cross multiply and divide. Okay. The other thing you could do, right, is mostly just say, okay, what do I have to do? What do I have to multiply or divide by 4 to get to 12? Right? 3. And so then I just create that fraction, right, out of 1. And once again, 3 times 3 is 9. So whatever I do to the bottom to get one number, I do the exact same thing to keep it in proportion. And then I can find all those equivalent fractions. 3/4 and 9/12 are equivalent fractions. Okay? Does that feel all right for everyone? Hopefully, yes. All right. Okay, so don't worry too much about adding and subtracting fractions. We're probably not necessarily going to have to work on that too much with our new current unit. Let me just fix that. Okay. Oopsie doodles. Okay. All right. So the most important thing that I want to talk about is in order to add or subtract fractions, we have to have what we call a common denominator, which means we usually have to use equivalent forms of fractions. And so, for example, if you look at this first one, okay, 1/2 and 5/8 do not have common denominators, so I can't just add them. However, I know that, right, there's an equivalent form of 1/2 as 8ths. So once again, I find that equivalent form, 1/2. What would that look like as 8ths? 4/8, good. So now I would take 4/8 plus 5/8. Okay. Now that I have a common or matching denominator, now I can add my fractions, and all you do is add your numerators and your common denominator stays the same. Now, of course, if you end up with an answer that's an improper fraction, usually then you would move it into or treat it as a mixed number for your answer, but of course it depends. Subtraction works the same way, right? If I have unlike denominators, I'm going to have to find an equivalent form. So if I say, right, 3/5 is the same as 6/10, and I can subtract tenths from tenths, but I can't subtract tenths from fifths. But now 7 minus 6 is 1, and my denominator stays the same. Okay? So like I said, you probably won't have to do too much of that for the unit we're going to focus on today, but I just want you guys to kind of have that refresher. What we are going to need to do for our upcoming unit on probability is multiply, okay? Does anyone know how to multiply two fractions besides put it in the calculator?
Multiply the top numerator and multiply the bottom.
Yep. I got what you're saying. Good. And so it's actually really not hard. I find that multiplying and dividing, well, especially multiplying fractions is way easier than having to do all this common denominator stuff. So yeah, you're just going to multiply across the top. 5 times 4 is 20. Oops. and 9 times 7 is 63. Then I'd have to figure out if that's reduced. I think I cannot reduce that anymore. Let me see. 20. Yeah, I'm thinking no, especially when you have an odd number in the bottom, unless it's kind of a funky famous odd number, like has a 5 or something. So once again, just multiply your numerators, multiply your denominators. It works just the same if you have 3 numbers instead of 2 numbers. For dividing, that's where you have the most of the time where you have to apply the reciprocal. So in order to divide fractions, you're going to take the second value and take the reciprocal. And when you do that, your dividing becomes multiplying. So if you have 8/15 divided by 7/12, then you would. Okay. Now, the other thing you can do when you multiply fractions is you can look at the crosses, like the diagonals, the 8 and the 7 and the 12 and the 15. And if you want to reduce it here, same way, right? You can kind of reduce it either place. So here, if I see a 12 and a 15, I can take a 3 out of here. 12 divided by 3 is 4, 15 divided by 3 is 5. Now, when I multiply, I get 30 bits. And I think that's as reduced as we're going to get. But pretty close to 1, right? 32 and 35 are pretty close together. Let's see. 32. Yeah, should be.
Wait, you said the 9, then.
Huh?
Oh, I did an extra, or I did times it, and I got 96 from 105, and then I got.
Yep. So I reduced at the beginning instead of the end. You can reduce on either side. Michael, did you have a question?
Oh no, I'm just testing.
Oh. No worries. I appreciate it. Just checking in. So yeah, so that was what I was mentioning there, Alyssa. Yeah, you could just easily multiply across the top and the bottom and then reduce. Usually if you cross reduce before multiplying, it usually saves you. It's usually easier to reduce the smaller numbers before you multiply them, but if you have the heavy lifter, you don't have to worry about it. So whichever way works for you. Yeah?
Yeah.
So. All right. So like you said, don't worry too much about this, but I just wanted to kind of show you when you might see a reciprocal. This is going to be the most common place. And then of course, why do we need to find all these equivalent forms? What do we do with them? And those kind of things. So, okay. Wow. Sorry. All right. And that's the end. Okay. Any questions or confusion about our warm-up here? Okay, hopefully you feel like that gave you a good refresher. Cool, thanks, Angel. All right, okay. So, we're still in our math book now. I think Michael, George, I can't remember where you're at, but I'm not sure if you were able to pick up a copy of the math book. I still have some. If anyone needs to come to Flagstaff campus and get one, they also have some in Page.
I probably will have to come to Flagstaff and grab one.
Okay. How
Yeah.
far away is that? Is that something that you would be doing anyway, or is it
it's something I would do anyway.
Okay.
Too far.
Perfect. So yeah, if you come to the 4th Street campus on the east side of town, they have some at the front desk. So if you just say, Julie said I could come get my GED math book, they should know what you mean. And I still have some. So, especially for people who just like hard copies. And of course, we're already done with the first 2 units, but if you're, have any time, get snowed in or something, you can always go back and look at those other first 2 units. There's always the answers are at the end of each unit. Yeah. Okay. So if you do have your math book, then you can open it up and, all the PDF versions of our units are here. The full packet is here as well, just in a PDF, a digital form. But like you said, I'm kind of a paper kind of person. Okay. Oh. Okay. So before we hop into probability, we're going to do kind of a related topic to kind of, and George as well, if it's convenient for you to go to either campus, if it's going to be out of your way or like a special trip, I can send it in the mail if that would help anyone. Pardon? We are. So yeah, so we should be on page 63 for our unit 3. And so, like I said, before we get into probability, we're going to do one related topic, and it has to do with these counting problems. And as we look at some of the examples, you might start to recognize them, but once again, kind of a helpful one to know. Okay. So this is page 64. You'll see the 64 in the bottom middle of the page. Those are kind of our official page numbers, although there's other page numbers that kind of show up, okay? All right, let's see what we've got. So a counting problem asks you to count the possible ways something could happen. Okay. And so that's where we're going to start. Excuse me for just a second. Sorry. Okay, so let's look at this example. The Parkers are taking a photograph of their 4 children. They have Alan, Bianca, Callie, and Dennis. Very interesting names. And they plan to stand in a line. So how many different ways can the children line up? Okay, so you might have seen some problems that look like this. And so basically we want to know how many combinations, right, of Alan, Bianca, Callie, and Dennis exist, right, for, oh, now I get why they're called, because it's A, B, C, D. Okay, now, see, I'm slow, guys. You probably already noticed that, okay? So, of course, the easiest, maybe not necessarily, it's not the easiest, but the most straightforward way to begin to figure that out, right, is to begin to, right, basically write out the different orders, okay? So if we start with Alan first, we can just go A, B, C, D, but we could also go A, B, D, C. We could also go A, C, B, D. We also could go A, C, D, B, A, D, B, C. So, right, even just with Alan as in that first order, okay, we already have, right, 6 different ways of lining them up, right, just with Alan in that first position, okay? And so we would equally have, right, 6 combinations with Bianca, right, in that first spot. Same for Callie and same for Dennis. So in all, there are 24 possible ways to arrange the 4 kids, okay? Not very enlightening, earth-shattering information, and I'm sorry for my crooked scanning. Hopefully you don't hurt your neck. But good, okay? And so if you carefully organize your work, you can often see a pattern that can help you count the possibility. So once you know that there are 6 ways that start with Alan, you can conclude there will be 6 ways for each child, which would be 6 times 4, 24 possible ways. Okay. And so you can kind of make a table. You could also, right, make an what more of like a diagram, depending on what you've got. So here's another pretty classic example of these style of problems. Emily wants to wear red, white, and blue for a holiday. Must be election day coming up. She can choose from 2 pairs of sneakers, white or blue, and she has 3 shirts, red, white, or blue, and then 3 pairs of shorts, red, white, or blue. Okay. And so if she wants to wear 1 red, 1 white, and 1 blue, how many outfits can she make? Okay. And so a diagram can help you see, right, that if I have white shoes, that means I can wear a combination of my blue shirt and my red shorts, or my red shirt and my blue shorts. Okay. And then, right, if I wear my blue sneakers, then that means, right, that I could wear a white shirt and red shorts, or a red shirt and white shorts. So here we know that with this combination of sneakers, shoes, and shorts, and how Emily wants to color coordinate, right, she can make 4 possible outfits. Okay. Now, of course, there is math, like calculating, that goes on in the background, but if you forget that, try to map it out. Okay. Although don't feel the super strongest about that either, but hopefully this is not feeling too crazy for everyone. Okay. So in the problems that follow, try some different strategies, create a diagram or a picture, okay, and look for organization, or look for patterns, sorry. So if we think about number 1, okay, a television network is planning its Thursday night lineup. It has 2 sitcoms, 1 drama, and 1 reality show planned for Thursdays. In how many different orders could the programs be shown? Okay. So how would we begin to, right, map this out? We've got that, that, and that. Okay. So we would start to kind of, right, organize our pieces together here. Okay. So I'm going to say, whoa, sorry. Hang on. Okay. So we've got sitcom 1, right? And so once again, with sitcom 1, it looks like I could do sitcom 1, sitcom 2, drama, sitcom 1, reality show. Okay. So that's, and then from here, right, we can do drama. I think it's gonna end up being similar to the kids, right? 4 kids, because we have 4 shows. Sorry, I'm getting stuck. There's 6 different combinations. Yeah.
Then.
Yeah. All right. I think that's what we're gonna get. Oh, okay. So, even though she left, Alyssa was correct, but I think, let me see here. I gotta get better at this stuff anyway, so I'm practicing with you guys. But basically, we could say I'm gonna start with sitcom 1, and sitcom 2, and then yeah, so we know basically for each show, once again, we're gonna end up with kind of 6 or yeah. Yeah. Okay, sorry. Keep getting distracted. So then the same would be true for our drama and for our reality show. We would have, right, kind of 2 different combinations of 3. So then we end up with 8 combinations of 3, which is 24 total combinations. Okay. So, no worries, Kristlyn. It happens. We did a warm up. We're now on page 64 in our book. Okay, let's look at the next one. Hopefully no one's feeling too frustrated right now. Like I said, there's let's see how we do here with number 2. Okay. Excuse me. All right, a car can seat 2 people in the back and 2 people in the front. A mother and her 2 children get in the car. How many different ways could the family be seated if the mother always has to be the driver?
Hello.
And you said 6? That makes sense, right? Because we have 2 kids, and each of the 2 kids can sit in one of 3 spots, right? Is that making sense, hopefully? A little bit. Since the mother's always going to move. Yes, right. And we basically have 2 people rotating between 3. Okay, let's look at number 3. Jan is ordering custom shirts for her business. There are 5 colors and 3 styles of shirts to choose from. So how many different choices does she have? We have 5 different colors in 3 different styles. So how many total choices are there?
Eight?
Huh?
Do I have
Well,
5 colors and 3 styles?
you're just gonna add the numbers. Brandon, you're good. Thanks. I'm glad you could join us for a little bit. Hopefully you got some learnings. Um, so yeah, so we kind of have, so really we just think about, we have style, what, sorry,
Color.
right? Style 1, style 2, style 3, right? And then for each we have color 1, color 2. So if we, for each style, we have 5 colors. If we have 3 styles, then how many total styles do we have?
15.
15. There we go. Yeah.
Oh, okay.
So multiplying is gonna be what we're gonna do because, right, the more we have to kind of create our combinations, right,
Mhm.
it's just gonna get more and more complex. So yes, 15 there. So that one wasn't too. Like I said, I don't know why my brain is really resistant to these problems. So like I said, it's good that we're learning together. Okay, in figure A, in the figure, excuse me, how many different line segments can be drawn that connect exactly to points? Oh. So, right, we kind of have to, that's a lot, right? So it's like, oh. That's 1. 2, 4, 5, 6. It's dark, right? And then we have 1, 2. Let's see. Now. So that's 10, 11, 12. Run out of colors. 13, 14, 15, 18. I'm gonna say 21, but I don't know. Huh? But now. Oh, wait, but now they're overlapping. It's down there. Because only D and F would need to connect there. Everything's connected to E. Yeah. Oh, okay, 20. For each of the first 5 actions, there are 4 possible second actions. I think we were getting there. I said 21, so I think I was only off by 1. All right, let's look at number 5 for fun. Ugh. Okay. The directions for a game say that the player must take 2 different actions on his or her turn. You can draw a card, play a card, take an action, capture an opponent, or buy an item from the bank. So we have to take 2 actions and we have 5 choices of actions, and we can't take the same action twice. The order that the player takes the actions matters. Moving and then playing a card is different from playing a card and then moving. Oh, what? Oh, ha ha ha. Okay, so kind of differently than our where like the mom's only in one spot. Or here, right, where they were saying like this is still 1 regardless of your direction. Now we can put it in any order. Oh, shoot. I gave you the answer for number 4 for number 5. Number 4, it says it's 15. Sorry about that. 5 plus 4 plus 3 plus 2 plus 1. Here, right, we have 2 actions and we have 5 actions. Or sorry, we have to take 2 different actions. We have 5 choices of action. So how many combinations of actions can we do? Okay. And so, right, if we draw a card, we have 4 other actions that we can do, right? And 4 other combinations of these. Okay. And since there's 5 total actions, then we would say 5 times 4 is 20. So there's 20 different 2 action turns possible. Okay. So basically, right, I can take these and make 20 different combinations of 2 action turns. Okay. So I'm sorry this doesn't feel super mathy, and I know it's very logic-y. We're gonna get into the math part of it probably on Wednesday. So don't worry if you're feeling a little bit confused, because like I said, this is not one of my strongest math areas, but we're gonna get through it. Okay. All right, let's look at number 6. Okay. The truck in the drawing needs to make a delivery to the house in the top right corner. If the truck must stay on the lines and only travel north or east, how many different routes can the truck take to get to the house? So
5,
5? Okay, how'd you get 5, Joe?
because it can only go north or east, so you can head north on the first line and then east and then go up north and then east
Mm-hmm.
twice. I mean, I just did it. I just did the lines
Good.
going north and
Good.
east.
Yeah, I don't, it's saying in the answers that there's 10, but we'll
I
have to
was
see.
like, I won't know.
How is there 10? 1.
Yeah, so 1,
Yeah, I did that line. Did that one.
2, 3,
Oh wait, yeah, there is 10.
and then 4, 5,
Uh,
6, yeah.
yeah.
She got half of them. So it says it takes 5 steps to get to the house. 2 will go north and 3 will go east, right? Regardless of whichever combination. Write the list showing all the possible placements for and north. So let's see, we got 5 total spaces. And we can either go 2 or 3. We're always gonna have to go 2. That's weird. Well, the answer says 10. And of course, the explanation isn't helping me explain it to you guys. Okay.
Zigzag.
Yeah. Who is this person? I know, like just do the straight line. So 4, 5, 1, 2, 3, 4. Wait, 1. Yeah, that's weird. I'm not getting. Sorry, I'm like, does this count 1, 2, or is it like 1, 2? I definitely know 5 plus 3 plus 2 is 10, but should have studied more. I'm sorry. Maybe when we start seeing the math, then maybe that will help us. All right. We'll keep working on these. Don't worry too much. We got about 10 minutes left anyway, so we'll keep slugging through this, and then on Wednesday, I promise I'll study more. All right, let's keep going. Let's look at page 66. Okay. So what we've been kind of talking about, as you can see here, is when we count the possible ways, okay, sorry. In the last lesson, you counted the possible ways that 4 children could line up for a photograph. A way was considered different if the children were in a different order. When order matters, you're counting the number of permutations. Okay. I don't think you'll see that word like in the question, but once again, hopefully you can kind of recognize these situations once again, you're trying to figure out combinations of things when order matters. So in real life, the word combination is often used really when it's a permutation. Doesn't matter when you use a combination lock, you have to enter the numbers in a certain order, okay? So a combination lock should really be called a permutation lock, right? Because you can't just, you have to put the numbers in the correct order, or you're not going to have your lock unlock. Okay. So we'll get to combinations, but for now, okay, we need to just remember that order of events or items matters. Okay. So let's look at this first example here, okay? So in how many different ways can a student arrange 5 different books on a shelf? Okay? So count the number of choices the student has for each space on the shelf, okay? So this is like space 5 through space 1, okay? There are 5 choices for the first book, but once we placed 1 book, right, for the next, right, we're only going to have 4 choices among our remaining books. Once we place 2 of our 5 books, right, then we only have 3 combinations, okay? And so after each book is placed, there is 1 fewer choice, okay? Okay. Notice how the choices count down after each book is placed. And so in our first spot on the shelf, we have 5 choices. and so forth. So basically, you take your number of choices, your number of positions for the book, and multiply the numbers together. 5 times 4 times 3 times 2 times 1. Okay. And of course, a calculator is going to come in pretty handy for that. Okay. And like I said, for some reason, when I get to the math, I feel better because I feel like I have some kind of formula to help me remember what to do. Okay. And so we know that there's 120 different ways the books can be arranged on the shelf. Okay. 5 books, 5 slots in the shelf, on the shelf. Okay. So we know that slot 1, we have 5 choices, 4 choices, 3 choices, 2 choices, and only 1 choice by the very end. Multiply those 5 kind of choice slots together, and that gives our total number of combinations, okay? And so here, right, to solve any permutation problem, simply, right, multiply the choices, okay? Study how this basic idea can be used to solve a more complex problem. No. Okay. All right, got it. Okay. 15 runners are in a race. Okay. We got 15 total participants in the race. How many different finishers can there be for first, second, and third place? Okay. So we kind of know how many total we have, and then it tells us, right, give us these 3 places. So count the number of choices. So there are 15 runners who could finish in first place. Okay. And of course, since we have 1 first place finisher, that means that we're down to 14 choices for second place and 13 choices for third place. Now we could, come up with all the combinations possible, but that would be a really big number. But here they're just saying, right, what is the combination of the 15 runners, and how could they all finish first, second, and third among those 15? So count the number of choices and then, right, multiply the choices. So I think the challenge is always the counting part, right? Making sure you know how many kind of, slots you have and how many total people you have. So here, for first place, we take 15 times second place, 14 times 13, third place, and we get 2,730. So there are 2,730 different ways that the 15 runners could finish the race in first, second, and third places. Okay. Hopefully that's feeling okay. Not too hard. So let's just look at this example again. Okay. Don't worry too much about these 4 down here. That's probably where we'll start. Okay. Will the choices always count down? Not always. Okay, so here, once again, when we have set spots that then one of the things fills in, then the following spot we have 1 fewer, right? But if we think about our lock here, okay, goodness gracious, guys. A bike lock has 3 dials, so that's our spots, right? The dials with the numbers, and each of the dials has 10 numbers, okay? And so, I know. To open the lock, you turn the dials. A number can be used more than once, so, right, each of these spots is kind of independent, right? They don't depend on each other. Our combination could be 10, 10, 10, or 1, 1, 1, right? So here, when we count up the number of choices for each of our 3 dials, our 3 spots, we have 10 total choices. So 3 slots with 10 choices each means that we have 1,000 possible combinations. Or excuse me, permutations. Okay. So if you want to, in preparing for class on Wednesday, if you want to look at the remaining problems on page 67, you can. But this is kind of where we'll pick up. We'll probably warm up with something like this and then just kind of jump back in. Or maybe we should go back and warm up, review again. I'll think about it. Okay. Any lingering questions or concerns before we're done for tonight? Okay. Well, I'm glad you guys could join me tonight. And yeah, we're going to just keep diving into this unit. And sometimes these kinds of combinations and permutation stuff, you'll see, especially on GED science as well as math. So it's good that we're getting a little double coverage. Okay. Michael, hopefully you felt good about class. Celeste, yes, I would say, if you want to kind of be fresh and ready to go, with what we're focused on, but it's not like mandatory homework or anything. But yeah, go ahead and work on those problems on 67.
And then I can do some of these things in practice on essential education, right?
I'm sorry, what was that?
Some of these things I can practice and stuff on essential education.
Yeah, you should be able to practice them on essential ed. Yeah. If you can't like find the lesson directly, let me know and I can assign it to you directly.
Okay, perfect.
Celeste, I'm not sure if you ever got a math book or not. If you can't come to one of our campuses to pick it up, then just let me know and I can mail it to you. But yeah, that's, and